In the last lecture, we talked about how to apply Gauss law, what are the steps, what is the symmetry, what should be the Gaussian surface. Those were those things that we discussed in the last lecture. Today we are going to follow the same process, and we'll try today to apply Gauss law to few problems. The first problem that we can take is, can we calculate using Gauss law what would be the electric field? What would be the electric field due to a point charge? And we'll have this point charge as, suppose, Q. So Q is the given charge. Because of this, what's going to be the electric field? Well, so our approach would be, we'll first try to figure out the symmetry, right? So let's talk about this charge. So Q charge is here, and we want to find the electric field at some point, suppose here, which is our point of interest. And the distance between this Q charge, which is here, the distance is r. Small r is the distance of point P, which is point of interest, point P here, point of interest, and we want to apply Gauss law to figure out the electric field. So what we should do at the first instance, we need to figure out what is the symmetry. So if this is the charge, we know that this is a positive charge. It's given, suppose here, mention it's a positive charge, suppose. So we know that electric field is going to go radially out. So electric field is going to be in this direction. Okay. Now it's in space. So what we should do, in this space, if we imagine this electric field, we know from our understanding that R is constant. If R is constant, the radius remains constant. The value of the electric field is going to be same everywhere, constant everywhere. So if we draw our Gaussian surface so that R is same, and that could only be possible if we draw a spherical Gaussian surface. We draw a spherical Gaussian surface like this, right? And the radius of this spherical Gaussian surface is r. So radius is r. So we'll just erase it, and we'll denote this Q a bit smaller, which is a source charge, and we'll point that the radius of this spherical Gaussian surface is r. Why? Because if r is constant, radius remains constant, E is going to be same. And we are interested to find the electric field at this point. Well, so we'll write here Gaussian surface. And at this point, we'll also try to indicate the area, right? So area vector, because in electric flux equation, we'll have the area. If this is that area on the surface, so remember this surface is three-dimensional. The surface, it's a spherical, the space is spherical, but if we take that, the surface of it, right, the covering it is all around, and we imagine this area, infinitesimal small area, having the area vector in the direction of electric field. Why? Because we know that this area vector is going to be, if you take that infinitesimal small sort of like square on that surface, the area vector is going to be radially out. Radially out is also electric field. Radially out is also dA. So the angle between these two quantities is going to be 0. Well, having made this diagram, now we'll try to figure out what is phi. So we know this phi is equal to this closed surface, we need to operate this dot product. So from our understanding of electric flux, we know electric flux is known as is equal to integration over the closed surface E dot dA. So this means that this net flux is equal to magnitude of E, magnitude of dA, and the angle between is theta, suppose. So it's going to be cos theta. So here we'll indicate this theta is 0 degrees. Why? The theta is the angle between these two quantities in this diagram. Well, now we find that electric field is constant. So we'll take it out of the integral sign. We'll take it out of the integral sign, and we are left with just, so this is what the equation is, and here we'll put 0 degrees. So cos 0 is 1, so we are just left with dA. Elemental area dA, the magnitude of this. Now if you are going to integrate dA, right, all around the surface, so we know that our understanding of the geometry, from geometry we know that the surface area of a sphere is equal to, taking the whole sum, is equal to dA is 4 pi, r is the radius, so it's going to be 4 pi r square. This is what we get as total net flux. Okay, so by Gauss law, we know that this total net electric flux is equal to the charge enclosed by epsilon naught. All right, and we know what is charge enclosed. Since we know this charge enclosed is the source charge, which is given positive charge. So this is Q. Source charge is Q. So our equation becomes, so this implies that net flux, which is equal to, we have evaluated, which is E, magnitude of electric field, times 4 pi r square. Now this should be equal to this Q, which is enclosed charge, over epsilon naught. All right, so we are interested to find what is electric field. So this would lead us to find what is the strength or the magnitude of electric field, which is going to be equal to, make this subject of the equation, this would go in the denominator, so it would become 1 over 4 pi epsilon naught Q divided by r squared. This is what we get, and this is the same result as we got from Coulomb's law. So the same result as Coulomb's law, we have applied Gauss law, and very effectively we have got that value. So take note of the steps, to see how we have applied it, and then we'll move on in the next video to another symmetry. We'll take other examples and we'll try to apply the Gauss law, and then we'll find the results. So watch the next video. Thank you.